All right, welcome back. So in a previous video on homelab projects, one of the ideas I suggested was playing around with CUDA programming just to get a sense of what it's like to program against GPUs and also understand a little bit about what's happening in the space of machine learning, since that is all the rage right now. So I thought I would take my own advice and dive into some CUDA programming myself. And so this video is going to walk you through the very beginnings of CUDA programming. Now, I am not a CUDA expert by any means. In fact, I literally just started playing with it, reading through the documents and going through the examples myself. So I'm hoping in making this video, I can share some of the learnings I had along the way that maybe only someone new to this space would think about. Because if you've been doing it for 5 or 10 years, maybe you just forgotten like the questions you ask, like, why is it like this? Or how does this work? So what we're going to do is we're going to walk through just some very basic CUDA examples. And one of the standard kind of hello world style programs that you see in the CUDA examples is doing vector addition. Now, I'm not even going to start with vector addition. We're going to start even simpler than that. And the reason for that is when I was going through this myself, I did the standard, hey, let's write some vector addition, compiled it, and I couldn't get it to work. And I literally spent hours debugging it for what was a very simple mistake or mismatch configuration with drivers and some other stuff. And so if I had just started simple, and I would have saved a lot of time. So I'm hoping to do the same for you. So what we're going to do is I have on the screen here, literally the most basic, like this is the hello world program you're going to write when you start with C. We're going to start with this and we're going to evolve it to, like, again, a relatively simple CUDA program and kind of show you along the way and introduce some very basic concepts. Now, I'm going to assume that you've gone through the task of installing the latest drivers and installing the CUDA toolkit. And there are various tutorials on NVIDIA's website on how to do this. In this case, we're going to be doing this on Ubuntu Linux. Just to kind of jump ahead to one of the biggest problems I had that cost me, like I said, several hours of time, is making sure the CUDA version of your NVIDIA driver and the CUDA version of your toolkit line up. So here I have Visual Studio Code in front of us, and I'm just going to show you quickly how you can check those versions. So you can use the NVIDIA SMI command, and this will tell you about kind of your driver configuration. You can see I'm currently running the 560 driver. As of this is the latest available that I have. And you can see the CUDA version is 12.6. So we just need to make sure our toolkit version is the same. So the next thing we're going to do is we're just going to check the compiler version. And so this is NVCC is the CUDA compiler, and you can see it is CUDA version 12.6. Now, when I first started playing with this, I had CUDA version 12.6 on the compiler, and I was running an old driver of like that had this showing at 12.2, and I got no errors. Like literally my code seemed to work fine. And it was only when I started like looking at the output did I realize the CUDA kernels, the pieces of code that run on the GPU weren't being executed at all. So before you get started, make sure you check this. And the first programs we're going to write are going to confirm this as well. So we have our hello world in front of us. So let's just be very simple and start there. So we will just compile it. Easy enough. We got a hello world. So we're off and running. So what we're going to do is we're going to take this very simple function and we are going to move our hello world on to run on the GPU. So just to back up a little bit, you'll hear the term kernel, and don't get it confused with like your OS kernel. The kernel are the little pieces of code that are executed on the GPU. So we're going to write a very simple kernel, and it starts with __ global, and I will call it So that's it. Now we have two print statements. Now the one thing is, what you have to understand is when you start to write these kernel functions, again, these are executing on the GPU. They're not executing on the CPU. And we'll get into talking about the differences between memory on the GPU and main system memory. Essentially, you can think of these as executing asynchronously. So to ensure you get the output, you do need to put another command in here to make sure we wait for it to finish up. So what we're going to say here is CUDA device synchronize. All right, so we put in the CUDA device synchronize. Now we actually need to invoke the kernel. And the way we do that is like this. You can't just call hello world. This won't work. So there is an additional syntax, and it is 3 brackets like this, and we're going to put 1 and 1 in there. And what this has to do with kind of the threading that is used to execute the kernel. Don't worry about it for now. So we will just compile this. And there you go. We got 2 pieces of output as expected, the hello world from our main function and the hello world from the kernel. Now, this is a super, I think it's an important exercise to do just to ensure that your NVIDIA drivers and toolkit are working. So now we've confirmed that, we can go on to actually writing some meaningful code on the kernel. Now, what I'm going to do from here is we will jump into the basic vector addition. It's a very good demonstration of showing how CUDA code works and how to write simple kernels. I'm not going to go through the exercise of writing it in C and converting it. We're just going to write a new kernel function that does a vector addition. So let me show you what that looks like. And by the way, this first one, it's not going to be perfect. We're going to write a simple one and we're going to talk about how it works and we'll evolve it from there. So I will just remove this. All right, so we've written a simple function that adds 2 vectors together. Now this is not going to be the final code because this is not what we want to have happen on the GPU, but I just want to talk about it for a second. First of all, as I've said, when we finally get this working, this code will be executed on the GPU. This code executes on your CPU. Now what we haven't done is populate these vectors. And we'll do that in a second, but the one thing to keep in mind is, imagine this code is running on the GPU, so this memory has to be on the GPU as well. So when you create and allocate these arrays and populate them, you basically need to populate them and copy that memory over to the GPU. Now there's a couple ways to do this. In here, we can use traditional malloc statements, or if you're doing C++, you could do new and allocate those vectors the way you would normally allocate them. And then there are CUDA commands you can use to actually copy the vector over to GPU memory. So think about it, like you have to kind of set everything up and move it over to the GPU and execute it. What we're going to do here is take a bit of a shortcut. So let's just say our vector size is going to be 10, and I'm going to set up our 3 test vectors. Now, instead of doing a series of mallocs and copies, there is a function called CUDA malloc managed. And what this will do is this will allocate memory, and behind the scenes, it will figure out how to move it to the GPU. I have done some reading and it suggests that this is less efficient than setting up the memory yourself and doing the copies yourself. But for the purposes of learning and just playing around, this is a nice helper. So that's what we'll use for today. So what we're going to do is we're going to use CUDA malloc managed instead of malloc to set up these 3 vectors. And so we'll set up vector A. And we'll just copy this for vector B and the result vector. And the other thing I'm going to do is I will populate these vectors with something just so we can verify that they look okay when we're done. So we'll just set everything in vector A, B1. We'll set everything in vector B to be 41 since we're going to add these together in the long term. And I'm going to set everything in the result vector to be something I would not expect to see. Perfect. So like I said, this will allocate the memory for these vectors and it'll ensure it gets moved over to the GPU at the right time. So we'll just update our call to add vectors. And we will do printf debugging on this one, and we'll just print the result. We will print the context of the result vector when this is done. And so remember, we need to wait for the work on the GPU to come back. All right, so it compiled and it ran, and it looks okay. We would expect 41 plus 1 is 42, and we have 10 of those. So that's great. Okay, easy, all said and done, video over. Now, actually, we basically didn't do anything special, and we didn't leverage any of the strengths of the graphics card. We simply moved a standard vector addition over there. But now let's kind of talk about how we modify this and take advantage of how the graphics card works. So to do this, let's kind of jump over to a diagram and visualize kind of what's happening up here a little bit. So We'll talk about it first. So as we get these two vectors and we literally just iterate over them one at a time. So in a traditional C program, you're going to have one main thread. It's going to go through each of these one at a time and add them up. And so the advantage of kind of running on the GPU is we can parallelize this. So what does that look like? So imagine over here, we'll just diagram this. Imagine these, I will put these boxes in. Imagine these are all our input vectors. We'll just do 5 of them. It's half of the array. So we have 2 inputs like this, right? And we are adding them. I'm just going to say this is part of vector A and this is part of vector B. We are adding these together. And we are putting them over here in the result. And so what's happening in the code we just looked at is execution is basically starting at the top right here and running all the way to the bottom. So your execution will scale with the size of your vector. Now what we really want to do is it would be really cool if you look at these are independent. Like you can add each of the rows in the vector separately. And so that's what we want to change this code to do. So we basically want to have, ideally, one thread for each row, but we'll get to that. We want to have one thread adding across here, one thread adding across here, and so on. Because then you could basically do the entire program in parallel and it'll be super quick. Now let's jump back and take a look at how we do that. So this is where we need to look at how we invoke the add vectors function. In this mystical NVIDIA syntax, it takes 2 additional parameters. The first one is the number of blocks. Now we'll go into what blocks are in a second, but let's just start with the second one because that's the most interesting thing. This is the number of threads to use when executing this function. You can see here, we have 1 thread. So basically this is no different than just running it normally on a CPU. There's nothing special here. So we could change this to 2. We'll make it 2 threads. And now what you're going to have is when this kernel is invoked, it's going to be invoked twice, once on each thread. So think about 2 threads running through this. So we're not going to get to the ideal state of, 1 thread for each row of the vector just yet. We're going to have 2. And just to confirm, let's take a look at what that looks like. For those of you freaking out right now because you're ahead, no, this is not exactly correct, and we'll get to that. But I just want to walk through it so you can see. Well, perfect. It worked. We got the same result, and it's twice as fast, right? Now, we're not measuring it, so I'm being a little sarcastic. But actually, no, we didn't do this right. So if you think about what happened, is imagine we had 2 threads executing here. Each thread ran through the entire vector size. So we basically did the same work twice. So you had 2 threads running through all 10 of these elements, doing the math twice. So we actually didn't benefit from parallelism at all. And in fact, maybe we got a little lucky because you had 2 threads touching the elements of these vectors, and there's no thread safety going on here, so that could have resulted in an issue as well. But this is a very simple case. So let's think about logically what we need to do to modify this to take advantage of having multiple threads. And let's go back to this diagram. So I will say, okay, we'll remove this, and let's say we have 2 threads here. Again, we have 10 elements, but let's say we just have 5. We basically want a way to say, okay, I'm going to say this arrow right here, this is thread number 2, and this is thread number 1. We basically want a way to say, okay, you, thread number 1, I want you to work on this row, and then this row, and then this row, and then you're done. And then you, I want you to work on this row and this row. So you want to somehow divide up the elements of the vector and tell which thread to work on each set of elements. And that's roughly what we're going to do. It's not exactly as I described, but we basically have to segment this. So as the threads are running this code in parallel, they're only looking at a subset of the data. CUDA makes this easy with some additional variables, global variables that are available. And so what we're going to do is I'm going to add those in and show you how this works. So the first thing I'm going to do is add an index variable. So this thread IDX is available to you inside the kernel. And thread IDX.x is the index of the current thread. So going back to this example, we're going to have 2 threads running. You can imagine you would have an index of 1 and an index of 2. So we're going to set the index to that. And then we're going to do one other variable. We're going to call this stride. And this is going to be, during each iteration of the loop, how far do we jump? Basically, you'll see we're going to replace our I++ with this. And we're going to use another variable. And this is the number of threads. Now I wrote here number of threads in the block. We haven't gotten into blocks yet, but just bear with me. So here we have the total number of threads. In this case, it's going to be 2. And this is going to be the index of the current thread, right? So we'll have an index of 1 and an index of 2. And so now we modify the loop to say, we don't start I from 0. We start I from the thread index. We still go up to the vector size. And instead of going 1 by 1 through the vector, because we'll end up with repeated work, what we're going to do is we're going to increment by the number of threads. So remember, if there are 2 threads, this will basically go through every other element in the array. And so what I'm doing is I'm going to add yet another print statement for nice printf debugging to show what's happening here. All right, let's give this a shot. So we will compile this and we'll run it. All right, so this looks a little different. And so here the output is exactly the same. Again, because I'm not timing it or profiling it, actually, you can't see that it ran twice as fast. But let's just look at what happened. So here is the print statement that was executing inside this loop. Remember, before we were each of the 2 threads, we have 2 threads, was iterating over the entire data set. But here we can see we have thread 0 starts at index 0 of the vector, and then it increments by 2. And so let's look at thread 0's operation. It works on index 0. Thread 0 goes to index 2, 4, 6, etc. And then you have our second thread 1 going at 1, 3, 5. So here you go. So you've basically taken the data set and you've cut it in half, and you've said, okay, the first thread, you're going to work on this subset of the data, and the second thread, you're going to work on this other subset of the data. And you didn't do that kind of subsetting up front. You're doing it just by manipulating the indexes and the increments as you iterate through the data set. So going back to this diagram, my kind of bad diagram here, right? Just to illustrate it, again, this is thread 0. You went here, went 0, 2, and there. So it just kind of jumped through. So let's just take this to its limit for this particular case. So we have a vector size of 10. Why don't we just set it to 10 threads? So I'm just going to set this to 10. And here we go. Just take a look at the thread count. We had 10 threads. We have first thread starts at index 0, and of course it increments by 10, but that just fails this test, so it never runs again. And so basically here for this particular test case of a vector of 10, we have parallelized each data element in the vector. And so here, like in this, we're not done yet, but here we have gone from iterating through the vector sequentially to having multiple threads iterate over the entire data set. Now we've broken it up and achieved the parallelism where we have a separate thread working on each vector in the data set. But there's still more to do, which is particularly important when you're dealing with much larger data sets. So to take this to the next level, we need to talk about the concept of blocks. And this is that first parameter we didn't talk about. So we set the number of blocks to 1. We focused on the number of threads. And the concept of blocks, this is one of the areas where it took me a little while to get my head around. So hopefully if I can explain that, you can understand it as well. But I found the best way to understand it is to kind of step back and think about like what is happening on the GPU. So to do this, we're going to go back or make another fancy diagram. So let's clear this out. And so let's make a GPU. We're going to make a box. Okay, so in a part of a GPU, so we have this, and this could be any style GPU. You have these units, and that you'll hear the term SM, and these are symmetric multiprocessors. And these are basically the workhorses of the GPU. So they can run many threads on them. They have local storage on the SM where the threads can communicate with each other. We're not going to get into that. Now, different GPUs have different numbers of SMs. So I'll just throw a couple in here for an example. So at least the references I have in front of me say Pascal architectures or a Tesla P100 GPU could have 56 SMs. So think about it. You have these SMs where the number varies by GPU. So if you buy a lower end graphics card, it's going to have fewer, higher end is going to have more. You want all the code to run like regardless. So you can't hard code for the number of SMs and the parallelism. And so you basically kind of want to build an abstraction layer. And this is where blocks come in. Now, what you do is, so we talked about the concept of threads before, right? And so the way it works is there's a concept of a block. And each block, I'm just going to call this a block here. Each block has multiple threads associated with it. I've seen different numbers. I think I've seen around 1,024 threads per block, and maybe a little off on that. But basically, each block, each SM can execute several blocks at once. And the blocks are an abstract concept, but think of it almost like a grouping of threads. So you have these blocks, they'll have threads associated with them. Now imagine your program, we'll go back. Here we said we have one block and 10 threads. What's going to happen is this block will basically get scheduled onto an SM for execution. But we're not taking advantage of all these other SMs sitting here. They're just sitting around. So this is where we want to leverage multiple blocks. Because you think like what's going to happen is you'll have multiple blocks configured in your code, and I'll say the graphics driver, I assume that's where it's happening, but I'm not entirely sure. It could be happening on the card itself, is going to figure out how to schedule and execute these. Now, you can imagine in some cases maybe you have, let's just look at a couple extremes. You have two blocks and it's like, great, I can run this here and I can run this here, and you get perfect parallelism. But you also have other programs using this competing with these resources. So you may end up with like this block executing and this block has to wait, but your program doesn't have to worry about that. Or to take another case, imagine you have a lower end graphics card with just one SM, and it's like, okay, well, here I have two blocks, but really I can only run one at a time. So I'm going to run this one, finish. I'm going to run this one and finish. From your program's perspective, it doesn't know. It's kind of operating through this abstract concept of blocks and threads, and it just takes a little longer to run. And then when you actually kind of set up, a set of blocks that are executing within your program is called a grid. I'm going to be clear, I am not going into all the depth of how to set up blocks and grids and the multi-dimensional structures around them. I'm just trying to give like a really, really simple kind of overview of this and show how we can evolve this program. So going back, we have one block and 10 threads. So let's say we want to extend this to 2 blocks, right? So this would give us 20 threads because we'd have each block with 20 threads in it. But again, this code is not set up right to take advantage of this, because once again, now we need to segment this data set by the block as well and take that into account. So you're basically further segmenting this data set so the threads in each different block can work on just their subsegment. And that's the next set of changes we're going to make. So the first thing we're going to do is update our index variable, and we're going to take block idx sub x, and this is the index of the current thread. Sorry, it's the index of the current thread block in the grid. So this is the index of the thread block. We're going to multiply this by blockdim.x, which is, as we see below, the number of threads in the block. And then we're going to add in the thread index. So that gives us our index. So now we've kind of brought blocks into the picture here. And then for the stride, basically how far to jump each time. Just need to make one little modification. We're going to add griddim.x, which is a weird term because this is the number of blocks we have. I know it's a lot. Let me paste in something. I found it to be helpful to go back and forth to these definitions a couple times as I was working through it. So let's try this again. But actually, so if you look at how we configured this, have a test vector size of 10. This configuration is 20 threads, so that probably doesn't help. So let's reduce this. Let's do 2 blocks with 5 threads each, which is a total of 10. So before doing that, let's actually update our print statement to show a little more information. So we're just going to add in the block information there. All right, let's take a look if that worked. All right, here we go. So we can see, let's just look at the output. Remember, we started with 2 blocks, 5 threads per block. So in theory, again, we should just have parallelism across the entire thing. So we see 2 blocks. We have block 0 and block 1. We'll start at the top. So block 0, thread 0, worked on index 5. Block 1, thread 1, worked on index 6. Block 1, thread 2, worked on index 7. You can kind of see what's happening here. And then block 0, thread 0, worked on index 1. So you can see how we've kind of added, I want to say, another indirection layer. This is kind of the complete way to set up your processing on a GPU, organizing your work into separate blocks, because coming back to this diagram, these blocks will allow this work to be executed across multiple SMs. Now again, for small cases, it doesn't matter. Imagine that this test vector was really, really large, and we'll get to that in a minute. This is where using the blocks and making the most out of the parallelism available to you will really come in handy. All right, so let's expand this problem for one more time. And what we're going to do is we're going to remove these as constants, and well, there's going to be constants a bit. We're going to calculate them a little. So what I'm going to do is I'm going to call this block size, but this is the thread count. So I will set this to, I'll call it 256. It could be bigger. I've tested it with up to 1024. So we're going to set that. And now we're going to calculate the number of blocks. And we're going to do that based on the input vector size. So we're basically going to divide up the input vector into a number of blocks. It's going to be the test vector size plus the blocks. We want the block size minus 1. Great. And now we're going to make this test vector size a whole lot bigger. Make it a million, 10 million. That's 100 million. So we'll give that a try. All right, with those print statements removed, let's take a look at the performance of this. And that was basically instantaneous. So let's see, it's less than a second. But this was with the optimal parallelism. So let's actually go back, and just so we can show for demonstration purposes, let's roll this back again to the base case of 1 thread and see how long it takes. So 1 thread took 7 seconds. Okay, big difference from sub-second, but let's bump this up to 2 threads, see if it gets noticeably faster. And there you go. So 6 seconds. So again, this is very coarse. I don't know if that's really represented, but it is improving. Go 3 threads. 6. All right. And we'll just put this back to the full solution. We'll do num blocks. And there we go. And instantaneous. Again, if you really want to kind of get into the nitty gritty of this, you can profile this and see exactly how much time is saving as you parallelize the problem more. But anyway, we're going to call it here. Again, a really quick introduction to CUDA. If you're new to it, I hope this was helpful and gives you an idea of something to play with, again, in your kind of home lab environment. And I think it's super useful to kind of play around and understand a bit about how kernels work, a bit about how execution works on a GPU, and again, fun for a couple hours, and maybe this is a jumping off point to more complex projects. Hope it helped, and we'll see you next time. But not so fast. After I had wrapped up this recording, I was walking around and I realized I had made a super common mistake in programming like this, and an almost embarrassing mistake, which was, and if you saw the comment earlier in the video, I allocated all this memory and I never put in the matching free statements. So just for completeness, this is what you need to do. And I feel really bad that I missed that. And that's it. We're done. I think I got it right this time, and I'm out. We'll see you later.